There we go. Okay. Well, let's open with prayer. Father, thank you for today. Thank you for the grace to be able to be here and study about this world that you've made. As we look at these formulas and how to write formulas, and there are lots of little rules and lots of little parts. Rather, you just give us clear minds to be able to think straight and to remember the things, the details. Help us to be able to sort them in our minds in the right way so that we can hold on to them. We ask this in Jesus' name. All right. Well, so I was telling the fellows here that you have 4 homework quizzes up. Okay. I'm just going to remind you, these homework quizzes are for you. Okay. Do them. Don't do them. I'm going to give you full credit no matter what, but do them, because these are the things that will prepare you for the test. So on them, it's all the problems we've been doing the last couple of classes. You may get to one and go, I just don't even know where to begin, I don't know what to do. Here's the thing that's really cool. If you will just highlight whatever problem it gives you and then Google that. There's some group that has done a video series for every single one of these problems, the exact problems. And so you just look at the video section and it's going to be the first one that pops up. You click on it and it's going to give you a 5 to 12 minute video of like how, 12 minutes is, I can't handle 12 minutes of how to solve a problem. So I take that little gear for settings and I tell it to go like 1.5 speed, so it's like flying through this thing, and I just pause it where I need to. But that's what I recommend, because that will show you exactly how to do these problems. When I took second semester chem in college, you probably heard me say I just had the worst teacher imaginable. And that was true. But I did really well. So how did I do really well? My book it was similar to yours. It only had like one example problem for each type. There's one problem I remember in particular. I had to have worked that problem 30 times. The same problem, because it's way harder than anything we're doing right now. But it had so many steps and so many parts that I would do it 30 times. And by the 30th time, I still didn't remember every, it wasn't like I had like this picture in my mind, oh, you just do this. I was genuinely working it, But by doing it that many times, it could have easily been different problems, but it gave me the repetition that I needed, the confidence, to where when I saw something else, it was just right there. So there's nothing for this but to just do them, just to do the repetition, okay? And again, if you're just not sure where to begin, you get hung up on something, the great thing about this is those videos are there and they can help you, okay? And if you still can't get it, then send me an email and I'll do my best to help you too, okay? All right. We're going to pick up, Lord willing, where we left off, and it means I need this. So, last class, we were writing some balanced equations, right? That's where we were, and that is something of an art, something of a science, and we need to be able to do that. So, our last problem was 2NH4NO3 yielding 2N2 plus O2 plus 4H2O. Y'all remember doing that one? Okay, so we're going to pick up with the next problem in your book. That's another even good thing with all this. Since I am working the exact problems in your book, you can go and pull up this video on Moodle of each day's class and look at how we walk through them then if you need that. Okay, so here's our problem. I've got the decomposition of C2H6, oh, excuse me, I have the combustion of this. I didn't see that. Plus O2 will yield water. Actually, you know what? I'm not even going to tell you what it's going to yield. This is a combustion reaction. I'd like you to tell me what this ought to yield. So C2H6, this is a hydrocarbon. That's all it's got. This is like gas in a tank, right? Okay, or in anything that you're going to burn. And this is called a combustion reaction because I'm combining it with oxygen. When I do you know what my two products are always going to be?
Carbon gas and water.
Not carbon gas. There's carbon in a gas, C something, and then water. What can my carbon combine with?
Oxygen.
Oxygen. So I get CO2 gas. This is, everybody who's concerned about a green earth, they're concerned about this. We're burning fossil fuels, we're producing carbon dioxide, a greenhouse gas. Never mind that water is actually a way more important greenhouse gas, but that's a whole other story. And so this is always what you'll get when you do a full combustion of a hydrocarbon. Now, this is not a balanced equation. Of course, that's part of our issue here, is we're going to try to balance this equation. So what would you like me to try? Where shall I begin? Write it down a little lower so that I got more space. C2H6 plus O2 yield CO2 plus H2O. What do you see right away that's has to be out of kilter?
Carbon has two.
Carbon has two. I only have one, so I've got to go at least this, right? All right, well, by the way, how do I keep track of all this? I mean, yeah, you might be able to do it just by eye, but we also can keep a chart, right? So I can do down here, I can go carbon, hydrogen, oxygen. I can look at my reactants, I can look at my products. This is always a solid way to go if you have a more complicated problem. So on this side, I have 2 carbons, right? On this side, I have 2 carbons. On this side, I have 6 hydrogens, right? So 1, 2, 3, 4, 5, 6. Over here, I have 2. We have 2. So what do I need to do? I got to balance this. This has to go by 3. Okay. Okay, so that brings me up to equivalent number here. How many oxygens do I have here? 2. How many oxygens do I have here? 2 times 2 is 4, and 3 times, I got 9, right? Is that right? No, maybe it's 7. It's probably 7. Okay. So, over here I have 2, over here I have 7. Well, that didn't work. So what do? Yeah, so I got 7 over here, I got 2 over here. What am I going to have to do?
Can you use fractions?
You can use fractions.
So then I have to be 2/3.
Help me, where?
No, 2/3 more.
2/3?
No,
That didn't seem right.
no,
Okay.
2/3. So it's going to be a fraction.
You think it's going to be fraction? Okay. Let's.
It's going to be 3.5.
You want 3 halves? Why do you want 3 halves?
And the other one.
You want 3 halves here.
Yeah.
3 over 2. That'll get me 6 divided by, why can't it give me 1.5? How many do I want? I've got 7 over here, right? I got 2 over here. I need 5 more. Yeah? How do I turn my O2 into 5? Because it doesn't want to do that, right? O2, every O2 represents 2. I need 2.5 of these, right? Something like that. So what does that come out to? It's 2.5 as a fraction. But all right, 2.5 is a fraction. Good. 2 times 2 is 4, plus 1 is 5. Over 2, right? So 5 times 2 is 10. Divided by 2 is 5. That would work out, wouldn't it? So let's do that. 1, 2, 3, 4, 5.
That's what I was trying to say.
Okay.
I just said the wrong fraction.
I got you. Now, I said that and everybody just kind of paused. I had a friend who taught math and he said, you know, they'll have these exponents, or questions on these tests with exponents and all this kind of stuff. Kids won't miss it because they can't do exponents. Kids will do it because they hate fractions. Everybody hates fractions. So, I looked at this and I went, okay, I need 2.5 of these, right? Because each one of these is 2. 2.5 times 2 is going to be 5. But I want to express my 2.5, right? And I don't want to write it as a mixed fraction. That's not going to do me any good. I need it to be a pure fraction. So I go, well, 2 times 2 is 4. If I just put that on top, I could do it this way. I could do 4 over 2 plus 1 over 2, right? And then that would equal 5 over 2, which is how we got where we were. But just in case later on you're like, well, I don't know how to do this. Well, here it is. All right. So, I look balanced, right? Life's good? Yeah. I just have one problem, and what is that?
Fraction.
I can't leave a fraction here. So how do I resolve this issue?
Find the next thing. Full number.
Yeah, how do I do that? How do I resolve this fraction? How do I get rid of halves?
You add another one.
I'm not going to add anything. It's going to be multiplication or division.
You multiply it by its reciprocal.
I don't have to do that. I don't have to go that much. I multiply it by 2. The other day we had way too many, right? And we divided to make it smaller. The smallest whole number. Here, it's just weird. If I multiply it by 2, so basically if I take this whole thing and multiply it by 2, right? Then let's see. I should get 2 C2H6, right? Plus, how many O2s? 5 O2s. Yields 4 CO2s. I'm not sure if using 2 markers at one time makes me geeky or cool, but probably geeky. And then 6 H2Os, right? Okay. Yeah, we may have the wrong answer. We've done something wrong, my friends.
Now you have 5 times 2 is 8 plus 6, you have 14 oxygens.
Yeah, we discounted our oxygens. Let's step back a step. I think we've got the wrong number of oxygens. Okay. How many is this? 3. How many is this? 4, so I need 7, right? And over here I've got 2. So I need, that's where we messed up. Somebody messed up, whoever it was. I need this to be over 7, right? That makes sense? I need 7, is that right? Nope, I take it back. My 7 needs to be on top. I need that. That's what I need. These only come in pairs, right? Every time I have an O2, I get 2 of them, right? But I only need 7, so I need 7 halves, right? So I divide O2 by 2, that gives me 1, and I need 7 of those. So that's how I get that number right there. So now I go and I do this thing that I said I wanted to do last time, and I multiply the whole thing by 2. And everything's the same except for this one, right? This is going to become a 7, which now should be balanced. Let's see how we did. C2H6 plus 7O2 yields 6 H2O plus 4 CO2. Life is good. All right. All right. Well, let's take on the next thing. Okay.
I have a question.
Yeah.
So in any situation where you would need to use a fraction, is it always going to be kind of like the same way you set it up? So if you need a certain amount of, let's say you need 9, you would put that in the numerator of whatever.
Yes. Yes. And then a denominator, whatever this is.
Okay.
And then at the end, we'll multiply and figure that out.
Okay.
That's exactly it. Okay. All right. So in a chemical equation, we can have more than merely the number of each element or showing its relationship in bonding. We can put more information in it, and that's a fairly typical practice, and so we want to do that. So, phases of matter. How do things exist in matter? On Earth, typically.
Solid.
Solid,
Right.
liquid, and gas, right? Okay, very good. There are certain things that do not necessarily, we don't think of them as existing as a liquid, but we think of them as existing in an aqueous solution. Okay, so they're in a solution of water. So you think of table salt, right? So I can think of table salt as just a solid. Then if I put it in water, it's not a liquid, but it's dissolved in a liquid. And so that would be called an aqueous solution. All right. So let's think about some of this. I'm going to take 2 Na. This is 2 sodium atoms, right? And I'm going to, or 2 moles of sodium atoms. I'm going to put an S here. This S stands for solid, okay? And now I'm going to combine that with 2 H2Os, right? And that's going to be a liquid. Water is my solvent in this case, right? And now that's going to yield something for me. It's going to yield NaOH, sodium hydroxide. And this is going to dissolve. These two parts are going to separate because this is an ionic bond. And so this is going to be in what's called an aqueous form or an aqueous solution. And it actually also, when this reacts, it produces hydrogen. Hydrogen 2. Hydrogen 2 is a gas, always a gas. Okay, so we would write this as a gas. So just so we're clear, this is a solid. Right? This is a liquid. This means it's in an aqueous solution. Right? And this is a gas. Okay. Let's balance this, by the way. Got 2 sodiums over here. What do I have to do over here?
Multiply by 2.
I got 2 here. What do I need to have on this side? Gotta have 2. Okay. How many oxygens do I have over here? 2. How many do I need over here? 2, and I have them. Good. How many hydrogens do I have over here? 4. How many do I have here? 2. How many do I have here? 2. So that's balanced. That's good. Great. All right. You feel decent about this right now? Okay. These terms are going to be with us. We'll be talking about them forever. We're just going to add them. I'm not going to reteach them and go on and on and on. I'm just going to, assume that you know them. If you don't, then ask. Okay. All right. There are a couple of other things that we can do, that we can represent in our formulas, our equations rather. So calcium carbonate, CaCO3, that's a solid. You encounter this all the time. This is in your bones, this is in seashells, this is in chicken eggs, okay? Very common, it's what we call ubiquitous. It's just like all life deals with this all the time. If I took a bone or a shell or anything like that and I added heat, this would decompose into some other things, okay? It would decompose into calcium oxide, CaO, and it would decompose into CO2 gas. Okay, so how do this I already said was a solid. What's this going to be?
Yes.
It's going to be a gas, so I've got to put a little G, right? And CaO, calcium oxide, is also going to be a solid. Okay. Now, I said, how do I get it to do this? Because if I just leave it on the table, it's not going to do this. What do I have to do? I got to heat it. Okay. So if I add some flames to this, how do I represent, adding heat to this? We don't just like act like we're in middle school and draw flames everywhere like kids do. We put, no, you didn't do that? All right. We instead put a triangle up there. Okay. Now that triangle is representing the Greek symbol delta, which in science we always use to represent change. So we have a change. In this case, we understand that delta means temperature. So we're adding heat to this, heat energy. Calcium carbonate, when I add heat energy, will yield calcium oxide, or calcium monoxide, and then CO2 gas. Okay. All right. Let me just give you another one just to see where you're at. Let's do NaCl. Do that? I don't want to. Gotta do an easy one for you. Maybe we'll do it with this. It'll happen on this. Okay, this will be a good one. Okay. CaCl2 plus AgNO3 yields CaNO3 2 plus AgCl. This is not balanced. First thing I want to do here is balance it. What sticks out right away? Being unbalanced.
NO3.
NO3. I've got two of them here. I got one of them here. I got to throw a 2 up. Well, now I've got 2 silvers. What do I do over here?
2, 2.
Got to have 2. Well, now I've got 2 chlorines. What do I have to do over here?
Nothing.
Nothing. It's already there, right? I got calcium. I got 2 NO3, 2 NO3, 2 silvers, 2 silvers, 2 chlorines, 2 chlorines. This bad boy is now balanced. Now, let's throw in some other information, okay? CaCl2 is in a solution of water, an aqueous solution. So what do I do? AQ. Okay. Silver nitrate. Silver nitrate is also an aqueous solution. When it reacts, it produces calcium nitrate, which is aqueous. Then it produces silver chloride, which is solid. So I put an S, right? By the way, when you do something like this, when you have a reaction, basically this is just a liquid. And that's a liquid, but then all of a sudden you get a solid, right? Okay, this is called a precipitate. We're going to cover that term in a minute, but it's worth introducing right now since we're coming across it the first time. So this is a precipitate. This kind of reaction is called a precipitation reaction. Okay. All right, now, this is what's referred to as a molecular equation. All right? This whole thing, which represents like everything we've done so far, is called a molecular equation. Think of it as in an aqueous solution, this CaCl2, calcium chloride, it doesn't stay as calcium chloride. As soon as it comes into contact with water, calcium has a positive charge, the chlorides have a negative charge. They come into contact with water molecules and they begin to interact. And what happens literally at the molecular level, okay, is that your calciums with a 2+ charge and your Cl's, each with a negative charge, will get surrounded immediately by water, okay? So in particular, this is positive, so we think of the oxygen of water coming here, because it has a slight negative charge, right? It will get completely surrounded by water. And so this is called dissociation. These two things that work together, think about table salt. It's a crystal, right? But then you stir it in water, and it dissolves, and the chlorine and the sodium, they dissociate, they remove away from each other, at least if you stir just a little bit. And you don't, they're both still there, you can taste them, but you can't see them. Literally the two atoms in that salt are being completely surrounded by water on all sides. Okay? So, you don't have to know this for right now for a test or anything like that, but this is why this does what it does. Okay? Something like this. Okay? And that's going to happen. So these two things get separated into their ions. All right? This is an ionic bond, an ionic compound from an ionic bond. This is an ionic compound from an ionic bond. This is an ionic compound from an ionic bond. This is not. That's a covalent bond that just formed a solid, right? So this represents stuff that are in solution separated. This stuff that's in solution separated. This stuff that's in solution separated. This is a solid. So we want to rewrite this not as a molecular equation, but as an ionic equation, okay? So we're going to rewrite this, and we're going to write each one of them separated. We're going to have their charges. We're going to do all that kind of stuff, okay? So, can you get started on that? I will catch up with you. They're doing it that way. So my Ca, what does that become? It's an ion. What's the charge in this ion? +2. Right. We actually, the way we write it here is 2+. So I've got my calcium ion. How do I represent it in terms of solid, liquid, gas, aqueous, whatever? Aqueous. Plus 2Cl, and each Cl has a negative charge, right? And it's aqueous. Plus, over here, what do I write? How many of these? 2. These silver ions, okay? NO3, do you know the charge on NO3? You can actually tell it from over here. Calcium had a +2 charge, right? So NO3, if I've got 2 of them to balance out the positive charge in this, it must have a -1 charge, right? So if that's -1, then silver must be -1. And that fits over here also, right? Or I'm sorry, +1. +1, right? You could also look at your periodic table at the oxidation states and stuff. And that'll help you as well. So 2 Ag plus 2 NO, and this has to be aqueous, right? Plus 2 NO3 aqueous, and what's my charge on NO3? It's negative, -1. And I'm running out of room. I needed it written smaller. In fact, I may just start the whole thing over because I'm gonna run out of room. Okay, so Ca 2 plus 2 Cl negative. Both of these are aqueous. Plus 2 Ag plus 2 NO3 aqueous with a negative charge. The silver has to be aqueous as well. That's going to yield for me calcium, right? And my charge on the calcium is still 2 plus, and it's still aqueous. Plus 2 now, NO3, and that's aqueous, and that still has a -1 charge. Plus, now this does not dissociate. Silver chloride is a solid, so plus 2 AgCl, solid. Okay. This is called a complete ionic equation. You will probably never show me a complete ionic equation in this class. I will never want this. You're going to be challenged to write the next thing. We're doing this as a step to what comes next, which is what's called the net ionic equation. Notice everything here should correspond precisely to what's up there. All I've done is I had 2 here represented there. Well, now I need to put it in front. Same thing here. The 2 there, it remains. 2 down here, I need to put it out in front. This remains a solid. So this is called a complete ionic equation. It shows me every single ion separated by itself, and then of course I have my one solid. You're pretty clear on how to get from step 1 to step 2. Okay. Now the next step is to write what's called a net ionic equation. You guys understand the idea of like a net versus a gross. Net is like what I have at the end. I'm not worried about how I got there, what I put in. I just want the final product. Same thing here. So what I want to do is cross out anything that remains the same on both sides of this equation. Okay? For instance, calcium plus 2 ion, aqueous solution. Calcium plus 2 ion, aqueous solution. That bad boy I got to get rid of. Will not be in my net equation. 2 chlorines, negative, aqueous solution. It's not. This had a state of change, right? It's now solid and actually went through a redox reaction and everything. So this is staying, right? In fact, maybe it would be good for me right now even to write it down below. 2 Cl negative aqueous solution plus something. Now over here, I have 2 silver ions plus 1 charge, aqueous solution. That doesn't exist over here. I've got 2 Ag solid, right? So I'm gonna write that 2 Ag plus in an aqueous solution. Okay. So this stayed, and this stayed. Now my NO3 in an aqueous solution, my two of them, I have it here. I have the exact same one here, so that's got to go. Okay, so that's gone. Now I go ahead and draw my line. The only thing I'm left with over here is my two AgCl salt, my silver chloride solids. That is my net ionic equation for this. Okay. That's how you do it. You start with your molecular equation, then you write down your complete ionic equation where you dissociate everything, and then you just cross out the things that are on both sides. Now, as you get better at this, more familiar with this, you'll probably get to the point that you don't have to do this. You can just kind of see it. But you do leave yourself open to making mistakes. If you do it like this, you will see it, because it'll all be written out. And one of the things that gets tricky is sometimes you'll have something like calcium on one side, and you'll have it on the other, and you'll want to just cross it out because it's there. But if it went from aqueous to a gas or aqueous to a solid, that state change means that it wasn't just a spectator. By the way, that's what we call these. You need to know that. These ones that are doing nothing, they're remaining the exact same on both sides of the equation. These are called spectator ions. They essentially do not participate in this chemical reaction whatsoever. You need to know these spectator ions. And they do not participate, they just sit on the sidelines and watch so we can remove them from the equation. All right. Well, let's see, I bet they give me another one. Practice. We could do practice, let's do it. Y'all want another one of these? Say yes. Otherwise, I'll just move on to the next one. Okay. Oh my goodness. What's this? Just one. What is it? Huh. I'm going to write this up so you guys can start getting it down. Okay. NaCl aqueous. In water. When I add electricity, we'll produce for me sodium hydroxide plus H2 gas plus Cl2 gas. Okay, so that is the molecular formula. I want you to write the complete ionic formula and then work down to the net ionic equation formula, okay? I'm saying formula where I should be saying equation. I apologize for that. What's my first step? What do I start doing?
Need to balance it.
Okay, is it balanced? It's not balanced, okay. So I got 2 chlorines over here, that sticks out to me. So I'm gonna put 2 over here. Now I got 2 sodiums over here, I better balance that. Now I've got 2 oxygens, right? So I better put a 2 here, which gave me 4 hydrogens. Here I've got 2, and 2 is 4, that looks balanced. You feel good about that? Okay, so I've balanced it. What's my next step?
A complete ionic.
I want to write a complete ionic. So, what's the first thing I write here? Somebody other than you.
Is it whenever you start separating all the
Yeah. So what's the first thing I'm going to write here?
2 and
2 Na. And what am I going to say about this Na? I need to say 2 things about it.
It's aqueous.
Okay?
And its charge is it plus?
Plus, yes. And then, what's the next thing I write?
Chlorine.
What about it?
Would it still be 2 chlorine?
Yeah, it's going to need to be 2. Okay, and what do I do?
Aqueous.
Aqueous.
And would it also be just plus?
Not plus. This is plus. This had no charge overall, right? It was neutral. So if this has a positive charge, and it does, then chlorine has to have a negative charge. All right?
How did you know if the first one was positive or negative?
Just look at where it's at on the periodic table.
So how do I know if it's positive or negative?
Well, because everything here wants to give up an electron so that it can build its valence shell. So this one has, what does it have? That's got 1, that's got 3, that's got 11 electrons, right? 2 in the first, and 8 in the second, and 1 in the third. So if I get rid of the 1, then I'll have a full valence shell. Okay. So 2 Na plus 2Cl plus
Would it be 2H2?
well, now is this ionic? This is water, right? It's just water as a liquid, so it's not gonna dissociate. So it'll just be 2H2O as a liquid, right? All right, and then I'm gonna do my electricity. And what do I get over here?
2 aqueous. And
Okay.
that would be a positive.
Yeah, good. Plus,
Would you separate the O and the H?
no, OH is hydroxide, so that's gonna stay together. OH negative. So this will be OH negative, and it'll be also aqueous. Okay? 2. Thank you. Yes, 2 of them. All right, and then the last thing, or last 2 things, I'm just gonna drop my H2 gas and my Cl2 gas. They do not dissociate, diatomic molecules of gas. And there's no charge on these. Okay. So that is my complete ionic equation, but it's not what I'm looking for. So my next step is to look for spectator ions. Something that stays the same on both sides. 2 Na plus in aqueous solution. Over here I have 2 Na plus in aqueous solution. That's a good candidate to get rid of, right? Now look at this. I got Cl2, I got 2Cl, I've got Cl2. That looks the same, but if I got rid of that, it would be a mistake, right?
Yes.
What's a dead giveaway that I do not want to get rid of that? I don't want to get rid of this. I want to keep it. What tells me that? Because here I'm looking at chlorine by itself, kind of.
One's an aqueous solution, one's a gas.
Yeah. Right. This is existing also as an ion. This is molecular chlorine gas, right? 2 of them bonded together. Okay, so that stays. Water, 2H2O. I don't have that over here, right? It's gone. And the 2OH, they're not over there. And the H2 gas, that's not over there. So, theoretically, if I just write this down below, we should have a balanced net ionic equation. 2Cl negative in aqueous solution. plus 2H2O liquid. When I juice it with some electricity, yields 2 hydroxide ions in aqueous solution plus H2 gas plus Cl2 gas. And now I just need to check. I've got 2 chlorines over here. Actually, I'll let y'all catch up, sorry.
If we see this on the test, would we be telling me whether it's aqueous, liquid, or gas?
Potentially so. So you're going to want to know some rules for that, right? That's going to come up here shortly. Okay. So these are 2 chlorine ions, right? I got 2 of them. The only ones on this side, I need it to balance. I have it here with my chlorine gas, right? Over here, how many hydrogens do I have?
2, 4,
4. How many do I have here?
1,
2. How many do I have here? 2. So I've got 4. So my hydrogen is balanced. How many oxygens? 2. How many oxygens?
2.
2. So this is a balanced net ionic equation. If you can do this problem and the one before it, you're in a good way. All right? You can practice them like going through the same problems. All right? Just don't look at the answer and just work it through. This is how you do all of these. They're not any harder than this, okay? It's just the thing that will get you, if anything, is you'll just forget to do it. This is, I mean, yes, all this is there, but this is the only thing doing anything. So we get rid of, what do we call them? Things aren't doing anything? Spectator ions, we get rid of those, okay? The only things that are going to spectate in something like this are ions, right? I mean, if there's a phase change, it's not a spectator, right? This is why chlorine stays, but sodium went. Sodium remains as an ion, chlorine had a phase change. Okay, well, let's go on to the next thing. Precipitation reaction. I mentioned that a little while ago, right? What happens in the precipitation reaction?
Forms a gas.
Pardon?
Gas forms a solid.
Yes. Okay, forms a solid, right? So we come to this concept of solubility. Solubility, it's the idea of will something dissolve, right? Can it dissolve? Will a molecule dissolve in solution? That's referred to as solubility. Some things have just incredible solubility, some things have limited solubility, right? Table salt, soluble in water? How much so? Depends on how much water I have, depends on how much salt I have, right? Is there a point at which I can't dissolve any more salt in water? Yeah, it'll just sit on the bottom. Think about this with tea, especially, well, you guys aren't from here, but you know, Texas is known for its sweet tea. So they just pour this water or this sugar in to give you diabetes, and it's disgusting. Like you can't, you go to like certain stores here and like, you can't drink this stuff. It'll kill you. not to me, but all right. So here you go. See, they're just pouring all of it that they can, and then eventually it just, and so different molecules have different solubilities. Some easily will dissolve, and others will not. And some have very limited solubilities, and some have no solubilities. Okay, so it's just this question of, will it dissolve in a solution? Well, guess what? If it's a solid, it's probably not. That's coming out of the solution, it has like no solubility. Okay. Substances with relatively large solubilities are said to be soluble. Okay, great. That's a weird word to spell. Soluble means it has a high degree of solubility. Insoluble has a very low degree of solubility. If in my chemical reaction I produce something that is insoluble, like maybe everything was soluble, it was all ions, they're highly soluble, but when I reacted it, one of them was insoluble, that's going to form a precipitate. Okay? Precipitates form when the product of a chemical reaction is insoluble. All right. Wouldn't it be good if you had some way of knowing whether or not something was soluble? So I gave it to you, I handed it out to you, it was sitting on your desk when you got there. If you're checking this out later at home and you don't have this because you weren't here in class for whatever reason, it's page 167 in the textbook. And so it's a chart that just shows us rules of solubility for different ions and then for their reactions. I'm going to erase all of this. Okay? So again, this is page 167 in the textbook. Now, it's telling you some stuff. It begins with this list of soluble ionic compounds. So basically, if you do a reaction and this is anywhere on the product side, it's always going to stay aqueous. It's never going to be a solid because these have just such high degrees of solubility. So NH4, that's ammonia, right? Lithium, sodium, potassium, rubidium, cesium, chlorine, bromine, iodine, fluorine. There are a couple exceptions, right? Like with fluorine, it says compounds with group 2 cations such as lead 2 fluorine or iron 3 fluorine. Those are not, but those are the only times. What am I saying? If you see fluorine, it's going to be soluble. It's going to be aqueous, right? If you see potassium, it's going to be aqueous. It's going to be soluble. So you've got that list there that shows that there are just a very, very few exceptions. Most of these are so common, and we'll use them all the time that you'll just know, right? If it's there in group 1 on your periodic table, lithium, sodium, potassium, like you know, okay, great. These are always soluble. I don't even have to think about it. But then you'll get down to something like sulfate. And so you'll see, well, whoa, sulfate, if it's reacting with silver or barium or calcium or mercury or lead or strontium, well, we don't deal with those very often. I better go check those. And so you'll just check this chart and you'll go, oh. And sometimes you'll run into a problem where like just things aren't working out. You're like, something's off. Check this, check the solubility rules. Okay, that's what's going to tell you. And that'll be where your answer is. Then you have a list of things that are insoluble. In other words, they almost never, ever dissolve. Okay. So you've got carbonate down there. You've got chromate. You have phosphate. Is that phosphate or is it phosphite? All right, and then you have a sulfide. And then hydroxides, unless they're with the group 1 cations, so sodium hydroxide, lithium hydroxide, those are going to form bases. They're always going to be soluble. But if it's with something else in it, then it's not going to be. Okay? So that chart is going to be useful. I don't expect you to memorize that chart. If you ever need it, I'm always going to give it to you. Okay? Always, always, always. So let's do, let's just do 2 Ki aqueous plus lead nitrate aqueous. Okay, and it will yield lead iodide plus KNO3 aqueous. All right. Yes, sir.
So question, because you put as aqueous, you don't need to put the water in the equation.
There is no water. Water's not reacting. We had that one with the sodium and the chloride and the water. The only reason that water was listed there is because water was actually participating in the reaction. That was the one where we were doing hydrolysis, adding electricity to it. And so it produced chlorine gas, it produced hydrogen gas, and then that oxygen combined with the sodium and a little bit of hydrogen to form sodium hydroxide. So water was actually literally a product, or excuse me, a reactant in that. When it's an aqueous solution, we can write water, but it would be like a beyond a bystander. It's just, it's not just, you don't have to mention it all. Just the fact that we say it's aqueous lets us know, okay, this is all surrounded by water. So 2 Ki, right? So I write this, I get 2K plus 2I. This has a negative, this is a positive. These are both aqueous, right? Come on, y'all gotta go fast. We can get this done. Plus lead, aqueous. What's the charge on nitrate?
-2
Well, check it.
is -1. We have 2.
Okay. So then if this is -1, then this has to be +2, right?
Yeah.
Okay. That's going to yield lead iodide plus potassium plus NO3 aqueous. Y'all haven't addressed my glaring error that I did on purpose here.
You didn't
No,
put
it's not
whether
balanced.
Oh, I'm balanced.
You didn't put whether it's aqueous.
I didn't put anything about this. Look up lead iodide. Tell me what lead iodide is going to be.
It is not balanced.
It's not balanced.
This is, you have 2K here.
Oh, no, I'm not balanced, am I?
And then you have to put 2 on the PV.
Oh, that's it. That was the only mistake. I did, and that's just, I wasn't even trying to. I just left that off on accident. So I got 2K here, right, aqueous,
Yeah.
and that's going to be negative, and then, I'm sorry, positive. Right, and then NO3, it's going to be negative, aqueous, get 2 of those. I'm balanced, but I haven't dealt with this. So look at your solubility chart. Okay, so I'm looking at lead and iodide. Iodide is listed as one of these soluble ionic compounds, right? Chlorine, bromine, iodine. But then I have this exception. So iodine will always be soluble unless it is compounded with silver, mercury, or lead. And in this case, it's compounded with lead plus 2, right? So this is soluble or not soluble? Not soluble, so this is a solid. So this is a solid. Okay? Okay. We got to know that. That's going to have a lot to do with this, what we're doing here. So now I'm looking for my spectator ions, things that are just remaining the same. What are they?
2A plus.
Okay. What else?
And then 2NO3.
NO3s. Okay. So then my net ionic equation is 2 I negative in aqueous solution plus my lead plus 2 in aqueous solution, yielding Pb I2 solid. This is cool. You want me to show you this? I can show you this. Okay, I'm going to go get some for civic. This battery dies, or this computer dies. Okay, let's do this. And precipitate, I want you guys to do silver nitrate plus sodium chloride. Silver nitrate plus sodium chloride. So AgNO3 in aqueous solution plus Na Cl in an aqueous solution. First thing I want you to do is predict. You got to predict what the reactants are. Okay. Then you got to balance it. Then you got to start working on all this ionic business. Okay. So go ahead and take a stab at that real quick. I grab a charger. Why do we have this problem up here at this point in time?
That's right.
What are we working on? Rules of solubility, right? So all this is aqueous. So something over here, you just know. Now you won't always know. You'll just be told to balance the equation. So you'll need to know or you'll need to check, right? So chlorine is soluble with everything except for, silver and mercury and lead. So that's a dead giveaway right there. So this is going to be a solid. This will be aqueous, right? If I go to balance it, 2 silvers, 2 nitrates, I'm sorry, 1 silver, 1 nitrate, 1 sodium, 1 chlorine, everything's good. Okay, so it's good. So I know that silver and chlorine are going to be participants in my net ion equation, right? Has to be. Since I know these are going to be down here, Ag and Cl, right? I can just write that. But my sodium, I know that's going to dissociate. I know that's going to dissociate, so I can just get rid of that, right? My nitrate, that's going to dissociate, that's going to dissociate, I can get rid of that. My silver remains, my chlorine remains, so I can just write Ag, aqueous, plus Cl, aqueous, right? Of course, my charge on my silver is +1, and on my chlorine, -1, and there we go. Let's try another one here. The reaction of potassium sulfate with barium nitrate. So potassium sulfate plus barium sulfate. Okay, so this time it's giving it to you as a word problem. So you're going to know some things. What's the chemical symbol for potassium? Okay. Nitrate. We've been dealing with a lot. What is it? NO3. Okay, good. What's the charge on my NO3? We know it a lot. -1. What's my charge on potassium?
+1.
Huh? +1. Good. Okay. If this had been something like calcium and it was +2, then this would be like CaNO3, but it's not. It's just KNO3. So that's good. So that's potassium nitrate plus barium sulfate. What's the chemical symbol for barium? It's over on the Ba, good. Okay, and sulfate, what's the symbol for sulfate?
Is it SO?
Should be SO4. What's the charge on sulfate?
-2.
You should have a page for that, right?
It's
I think it's on the back of your periodic table. You've got these polyatomic ion charts.
negative.
-2. Okay, good. What's the charge on, so where's barium at? Look at where it's at on the periodic table.
It's +2.
Should be +2, so this is balanced, right? Okay, so I look at it, this is good on my product, or my reactant side. Now on my product side, this is going to be a double replacement reaction. That's what this is called, where they're going to swap partners, at least in the, as we're doing this ionic business. So we're going to go KSO4. Now this had what charge? -2. Potassium has +1, so I need 2 of these, right? Well, now I got 2, I better have 2, okay? Plus, over here, I better have BaNO3, 2. Okay, good. Now, potassium nitrate. What's the rules for that? Is that going to be soluble or insoluble? It says here potassium, everything is soluble, 100%. So this is aqueous, the whole thing, right? Good. Barium sulfate. So we need to look at barium and or sulfate.
Solid.
Sulfate is soluble unless it's with silver or barium. So this is not soluble, right? So it's not going to be aqueous, this will be a solid. Good. Okay. K2SO4. Potassium, all of them are aqueous, all of them are soluble. And then barium nitrate.
Also solid.
Yeah, where's my NO3 negative? Yeah. All of these are soluble, so this is aqueous. Okay? While you're out, the one thing you missed was we looked up this, okay, we balanced this equation. We completed it and we balanced it. And then we said, okay, we looked this up. Everything with potassium is soluble, always. But sulfate on this, sulfate specifically says it is not soluble with barium. So we know that this has to be a solid. Then we just came over here and double checked. All of these are soluble, and potassium sulfate is perfectly soluble, so that's aqueous. So now if I want to, I can just go 2K plus aqueous, right? Plus 2NO3 negative aqueous plus barium sulfate solid is going to yield potassium. Oh, I don't have this balanced, do I?
Yeah.
Do I?
Yeah. K2.
Oh, K2, I'm sorry. Thank you. Goodness. K2, positive, aqueous, plus SO4 negative 2, aqueous, plus barium 2 plus aqueous, plus 2NO3 negative aqueous, and now I'm looking for spectator ions, right? I will cross those bad boys out. So what do you have for me for spectator ions? Is potassium a spectator?
Yes.
Yes. Is nitrate a spectator?
Yes.
Is barium a spectator? No, right? We've got a state of matter change, right? From solid to aqueous. And sulfate. Sulfate goes from solid to aqueous, right? So that's not a spectator either. So then, if we've done everything right, this should be BaSO4 solid going to Ba2 plus aqueous plus SO4 to negative aqueous. And let me just double check, because I've been known to be wrong. All right, what do we have for time? We have time. That is it. Yeah. Did I really do this backwards? How do I manage it? I wrote this 100% backwards.
Looks strange because you started with.
I know, I'm sitting here going, well, I mean, if it was in an acid or something, I could see it. This is 100% backwards.
So you just flip.
I'm just sitting here out going, how did I do that? Like, did I get dyslexic for a minute? Because it's written the right way on this page, but I inverted and I don't have any solution. It's not like I read the solution backwards. I just crossed the parts in my head. So this is exactly backward. Let me write this one more time before we get out of here, okay? Just so we have it. If you see me do something that dumb again, tell me. Huh? All right. Although I'm sitting here going, this ain't right, but it must be. It's written here. I even checked it and still saw it the same way. Okay, so we have K2 SO4 in aqueous plus barium nitrate NO3, right? And we got 2 of these. Okay, and so that's going to yield for me 2 potassium nitrates plus barium sulfate as a solid. Okay, good. So when I go to do this, I'm going to get my potassium ions, I'm going to get my sulfate ions. I'm not even bothering to write all that, I'm just going to circle them, okay? Plus my barium ions, plus my two NO3 ions, and it's going to yield for me 2 potassium ions plus 2 nitrate ions plus barium sulfate insoluble solid. I begin to cross out everything that is a spectator. That's a spectator. That's not. This is a spectator. Okay, and so what I get here is Ba 2 plus SO4, 1 or 2 negative? 2 negative. And these are both aqueous, right? It is going to yield for me barium sulfate, which is a solid. Everything should balance. Life's good. Precipitates there at the end. All right. When you would expect something like this on the product side instead of the reactant side is when you're dealing with acids or bases, not when you're just dealing in regular aqueous solutions. All right. Well, we got where we got. I need to mark where we got so that we can pick up their next class. All right. Remember that you got those homework quizzes. They're boogers. We're into the math-heavy part of life, okay? So start tackling them. All right. God bless you.